Welcome to U7L1 set theory. So this lesson is the first lesson in the probability unit. And in this lesson, we're going to talk about sets, how they work together, different properties of sets so that we can eventually use them to answer probability questions. So a set is a collection of objects. Each object is called an element of the set. Okay, sets can be either finite or infinite. A finite set has a distinct countable number of elements, while an infinite set does not have a distinct number of elements. So you can't count how many elements are in an infinite set, but you can in a finite set. So for example, the set of states beginning with the letter O is finite because it just consists of exactly 3 elements, that is Ohio, Oklahoma, and Oregon, while the set of prime numbers is infinite because there are infinitely many prime numbers that exist. 2, 3, 5, 7, 11, and we can keep going and we will never be able to stop naming those prime numbers. Okay, so again, finite, I can count exactly how many elements. For example, 3. Infinite, I cannot count how many. There's infinitely many numbers or elements in that set. Okay, so here in the infinite set, it never ends. Okay, you have to keep listing forever. All right, a capital letter is used to define a set, and the elements are listed within curly brackets, okay, such as B equals, and then we have our curly brackets with the elements 2, 4, 6, and 8. Now, there's a special name for a set that doesn't have any elements at all. So the set with no elements at all is called the empty set, which hopefully makes sense because it's empty. Oh, that's already there. Okay, empty set, and is denoted as either a circle or like a 0 with a line through it, or just these curly brackets, but with nothing inside of them because it's empty. Okay, let's keep going. So then the universal set contains of all possible elements for a certain situation or scenario, and it's denoted as a capital U. So the universal set would be, for example, if I said, okay, in this problem, we're going to talk about all the months in a year. That would be the universal set. Okay, one example of a universal set is the set of all days of the week, for example. So that universal set would look like this. We'd have a capital U equals, we'd have our curly brackets, and then we would list all the days of the week. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and lastly, Sunday. Okay, and of course, this is a finite set because there's exactly 7 elements in that set. All right, the complement of a set is the set of all elements that are in the universal set but are not in set A. So the complement of set A is all of the elements that are in that universal set but they're not in set A. This is denoted one of 2 ways. I tend to use the first one more often. So A prime, okay, kind of like we used to see with when we did translations and transformations, right? Or we can do A and it has a line on top. Okay, those both mean the complement of a set. Okay, the complement of a set, which again is everything that's in the universal set but is not in the set that we're talking about. So for example, if we have a set U, that's our universal, with 1, 7, 10, 17, and 20, and then we have a set A with 1, 10, and 17, then the complement is everything that's in that universal set that's not in A. So meaning that it can't be 1, 10, or 17. So it can't be 1, 10, or 17. Everything else is in the complement of A. So A prime, which is equal to A with the line on top, is equal to, so the complement of A is the curly brackets with just what's left that's not in A. So that's going to be 7 and 20. And there's our complement. All right, the intersection of set A and set B is exactly what it hopefully sounds like. It's what they have in common, okay? So it's going to be the set of all the elements that are in both A and B. Okay, that's the intersection. It's going to be everything that's in both A and B. It's denoted as A, and then it kind of looks like an upside down U, and then a B. That upside down U is smaller, as you'll notice, okay? And it's in between both of them, kind of where you would have like an equal sign if it was an equation. Okay, so that means the intersection, and that's everything that's in both sets, what they have in common. Okay, so for example, given A equals, and I have a set there, and then B equals, I have another set, we're going to find the intersection of them. What do they have in common? So I usually start with my smaller set, and I just start looking in order. So I would start here because the set looks like it has less numbers, and I would just go in order and see if the numbers here, right, in A are also in B. So A has a 2, B also has a 2. So that's in common. A has a 6, but B does not. So that's not in common. A has a 10 and B also has a 10. So that's in common. A has 13, B does not. That's not in common. A has 17 and B has 17. So that's also in common. So they have 3 elements in common. Those are in the intersection. So that means that the intersection A and then that little upside down U, B, the intersection equals the set, so curly brackets, 2, 10, 17. And it is common practice to write whenever your set is numbers in order, right, from smallest to largest, okay? So there's our intersection. Now the union of set A and set B is the set of all elements that are in A or B. In A or B. So any element that exists in either one is going to be in the union. It's all possibilities. It's all possibilities. So it's not what they have in common. It's all possibilities. And the way we denote the union is just like intersection. Okay, except this one to me makes a little more sense. It's A and then it looks like a little U and then B. So I remember that as union starting with a U. So the one with a U is union. And the one that doesn't have a U, that's like an upside down U, is intersection. All right, so this one is not what's in common. It's all possibilities. So any possibility that shows up in either set is in the union. So this is all possibilities. So for example, if we look at sets A and B, and these are the same sets as above, we're going to put every possibility in the union. Okay, so if it shows up in both of them, you only write it once in the union. Okay, so if it shows up in both, write it once in the union. So our union is going to be A and then the little u and B equals. I'm going to start with the smaller one, A again, and I'm just going to go in order. And then I'm going to jump from one set to the other to make sure that I stay in order, right, in ascending order. So the first thing I notice that is in either one, the smallest number is 2. Okay, it's in both, so I don't need to write it twice. So I'll cross out the 1 in B. There's no 3, but there's a 4 in B, so I have to put that here. Remember, this is all possibilities. There's no 5, but there's a 6 in A. There's no 7, no 8, no 9, but there is a 10. And it shows up in both, but I only write it once. There's no 11. There is a 12, though, in B. Okay. There's a 13 in A. There's no 14, no 15, no 16. There's a 17 in both. I'll only write it once. There's no 18. There's a 19 in B. And then there's a 23 in B as well. No other numbers in between 19 and 23. So those are all the numbers that show up in either set. It's all the possibilities. All right, continuing on, we have a subset. Let's talk about what a subset is. So a set is a subset of another set if all its elements are contained in the other set. So a subset is saying, okay, in this set, this smaller set has to be smaller. Everything in my smaller set is also in my larger set. Okay, so B is a subset of A would be denoted this way. So B would go first because it's the subset. Subset is, it kind of looks like this sideways, it kind of looks like a C, sort of. Okay, it's going to be like this little sideways U thing with a line under it. That means that B is a subset of, and then we put set A. Okay, so B is basically contained inside of A. Everything in B is also in A. So it has to be everything in B has to be an A, not just some, everything. So for example, given A, 4, 7, and 11, and B, which is a bunch of numbers, it says A is a subset of B. A is a subset of B, meaning that everything in A is also in B. Everything in A is also in B. And the reason is because all the numbers in A are also in B. And that's the only way that a subset can exist, if all of the elements in one are in the other one as well. All right, so now let's look at some Venn diagrams which show up quite a bit in probability. So if you have a highlighter, I would maybe do this with a highlighter. Otherwise, you can just lightly shade with your pencil. So we're just going to go ahead and shade each of these examples. So we're going to shade set A. Set A is anything that's inside the circle that is labeled with an A. So anything in this circle would be considered set A. There can be numbers in there. There can be words in there. It just depends. Anything in there is in that set, okay? For the complement, if you remember from the first page, right? Complement is everything that's in the universal set, but not in A. So we'll shade everything in that box, which represents U, but not in the circle A itself. So everything in the box except the circle itself. Okay, so everything in the box except what's in A, which is the circle. Okay, so everything else gets shaded in, and that's the complement. So it has to be in the box itself, but not in the circle, okay? That's a complement. The intersection is everything that's in both of them, right? What they have in common. So that's where the two Venn diagram circles intersect. So it's where A and B intersect. So it's this little section here in the center. Okay, that's the intersection. So any values that exist in both A and B, they go inside the intersection, which is where they overlap, okay? Now the union means it can be in either one, right? So I have to shade in everything in A and everything in B. So everything in A gets shaded, okay? Part of B, is already shaded, right? And then I shade the rest of B, all of this, okay? All of that gets shaded because all of that is in the union. Anything that is in A or B, all the possibilities. Okay, so now let's answer some examples using sets, subsets, complements, unions, intersections, some Venn diagrams, all of that stuff, okay? So for example 1, it says, for each set, write out the elements and state whether it's finite or infinite. Okay, cool. So we're going to write out the elements, and then we're going to state whether it's finite or infinite. So set M is the set of all months in a year. So that means that we have to write 12 things out, right? Because there's 12 months in a year. So M equals, and use your curly brackets, we have, I'm going to go ahead and do shorthand. January, Jan, February, March, April, May, June, July, August, September, October, November, and December, okay? And I know it's finite because there's only 12 exact countable, right? It's a countable amount of months, okay? It doesn't keep going forever. There's exactly 12. So this is a finite set, and I know it's finite because there's exactly 12 of them. Okay, looking at the next one, set T. It's the set of all multiples of 2. So set T equals the set of all multiples of 2. So starting with 2, we have 2, 4, 6, 8, 10, 12. And I can keep going and going and going. So I'm just going to put comma, dot, dot, dot. Because the multiples of 2, they never end. You can keep going forever. There's infinitely many of them. So this is an infinite set. Infinite set. Okay, I can't count it. And then for the last one, it says set A is the set of all multiples of 2 that are odd. So it's the set of all multiples of 2 that are odd. So basically, it's everything that's already in this set of all multiples of 2, but that are odd. But that's a contradiction because multiples of 2 are always even. By definition, they're even. Okay, all numbers that are divisible by 2 are even. So this is actually not possible. So this is actually not a possible thing. So if it's not possible, that means there are no elements in that set at all. Okay, there's no elements in that set. So that means that A is actually the empty set. So I can either write A equals a 0 with a line through it, or I can write that A equals 2 brackets that are empty, right? So this is actually the empty set because it's not possible. All right, example 2, let's keep moving on. So example 2 says, find the complement of set G given sets U and G below. So U, remember, always stands for the universal set. And then in this case, G is going to be a set inside of that universal set, okay? So G here, it gives us 4 numbers, negative 5, 0, 2, 3. And then it gives us U, which is the universal set in this case. And we're trying to find the complement of set G. So the complement of set G, remember, there's 2 ways to write it. We can write G prime, or we can write G with a line on top. Either one means complement. So both of those are the complement of G. And it's going to be everything that is in that universal set, but that's not in G. So everything not in G. So negative 5, cross it out. 0, cross it out. 2, cross it out. And 3, cross it out. It's everything else. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And that's what's going to be in our set here. So our set, and go in numerical order, right? In ascending order. So negative 9, negative 3, 1, 4, 7, 11, 12, and 13. And that is the complement of G. All right, moving on. So example 3, excuse me, I almost skipped a whole example. Example 3 says, given sets J and K below, find the intersection and union of J and K. So intersection and union. So remember, intersection is A, and then that upside down U, B. Oh, it's not A and B, it's J and K. Let me use the correct letters here. So J, upside down U, that means intersection, and then J with the one that looks like a U, K means the union. Intersection is what they have in common, and the union is all possibilities. Okay. All right, so let's take a look. So let's look at the intersection first. So I always start, like I told you, with the smaller set, which in this case looks like K, and I go ahead and just start looking through and seeing what they have in common. So K has a 3, but J does not, so that's not in common. K has a 6, and J also has a 6, so that's in common. I'll circle that. K has a 9, J does not. K has a 12, J also has a 12, so those are in common. K has a 15, J does not. K has an 18, J also has an 18, so that's in common. And then K has a 21, J does not have a 21. So they only have 3 elements in common. So for the intersection, J intersect with K, it's going to be equal to the set of 6, 12, and 18. So just those 3 elements are what they have in common. And then for the union, it's all possibilities. So it's everything in one set and everything in the other set. We just don't write the duplicates more than once. Okay, so starting with the smallest number I see a 2 first. So I'll put that first. Then I see a 3. There's a 4. There's no 5, but there's a 6. And again, it shows up twice, but I don't write it twice. There's no 7, but there's an 8 in J. There's a 9 in K. There's a 10 in J. There's no 11 in either, but there is a 12 in both, so I'll write that once. There's no 13, but there is a 14 and a 15. I see both of those. I also see a 16 in J, so I'm writing that one. There's no 17, but there's an 18, so that one shows up. And then there's a 20 and a 21, and that's what's left. Okay, so that's everything that's possible from J or K. Okay, so that's the union. Oh, I wrote this wrong. Make sure you fix that if you did what I did. So that's the union. This is the union. So it's all possibilities. So make sure that you fix that if you wrote it wrong. Okay, so this is the union. Okay, perfect. Let's look at the next one. For example, 4, it says, for each pair of sets, determine if one is a subset of the other. If yes, describe the relationship using proper notation. So remember, a subset can only occur if everything in the smaller set is in the bigger set. Every single thing in the smaller set is in the bigger set, okay? Has to fit perfectly inside that bigger set. So let's take a look. So the first one says S equals letters in the word sigma and A equals letters in the alphabet. So it looks like the word sigma has less letters than the alphabet. So the only possibility is that S is a subset of A. And let's see if it is. S is the letters in the word sigma. Are all of these letters also in the alphabet? Yes, they are. So yes, the answer is yes, there is a subset, and it is S. S is a subset of A. Remember, subset is like this back sideways U with a line under it. Okay, and that's because all the letters in sigma are in the alphabet. Okay, all letters in sigma are in the alphabet. Okay, and that's the reason why. All right, let's look at this next one. It says A equals the months with exactly 30 days, and B equals the months that start with the letter J. So the months with exactly 30 days, there's quite a few of them. Hopefully you know which ones have 30 days. I have a trick I can show you in class for sure that I learned when I was a kid. But there's quite a few months with 30 days. The only months that start with J, though, if we go through the alphabet, or not the alphabet, the months of the year are January, okay? And then we have February, March, April, May. We have June and July. Those both start with J. And then August, September, October, November, December. That's it. So there's 3 of them. So there's only 3, okay, elements in set B. And of those 3, again, I'll have to show you the trick if you'd like to know. January has 31 days. I'm looking at the trick. I'm using my knuckles to do it. June has 30 and July has 31. So the months that start with the letter J have 31 days, 30 days, and 31 days. The months with exactly 30 days, there's only one that actually fits that, correct? There's only one that fits that, and that's June. The other 2 do not. That means that B is not a subset of A because it doesn't actually fit. And A can't be a subset of B because, again, that doesn't fit. The months with exactly 30 days, there's a bunch of them, and they're not all listed here. Okay, so this can't be a subset of that. So it looks like there is not a subset that's existing here between A and B. So I'll just write no. That's all we need to put there. No. And the reason is because January and July, they don't have exactly 30 days. All right, let's look at example 5 here. So example 5 looks like it's going to be a Venn diagram. All right, so example 5 says the universal set U consists of the natural numbers that are no more than 16. Set P is the perfect squares in U, and set E is the even numbers in U. Label the Venn diagram below. Fill it in, and then answer parts A through D below. Okay, so this will be the end of the notes. So taking a look, it says the universal set consists of the natural numbers that are no more than 16. So natural numbers, if you don't know the definition of natural numbers, this is very important because this could pop up again for sure. It's whole numbers from 1 on. So non-negative whole numbers. So it's whole numbers, okay, 1 and then greater, 1 and greater. Actually, I guess I can write it like this, greater than or equal to 1. Okay, whole numbers that are greater than or equal to 1. So 1, 2, 3, etc. It says that are no more than 16. So no more than 16. They can be 16, but they can't be more. So that's 1 through 16. So my set U, I'm going to write this right above our box, is going to be all those whole numbers from 1 to 16. So 1, 2, 3, and list them all out all the way to 16. I would not skip this step if I were you because you're more likely to make mistakes if you skip this step, okay? So I'm listing out that universal set, which in this case is natural numbers, whole numbers that are greater than 1, or greater than or equal to 1, and not more than 16, okay? So that's 1 to 16. All of those numbers have to be in our universal box. That means all of those numbers are going to have to exist inside this box somewhere. Some of them are going to be inside P, some of them are going to be inside E, some of them are going to be inside the intersection, and some of them are going to be outside of P and E because they actually don't exist in P or E, but they're still in that universal set. So they'll be out here in this space, okay? All right, it says set P is the set of perfect squares. So any number that has a square root, that's a whole number, right? And then set E is all of the even numbers. So we're going to fill in everything in the diagram. I suggest to just go in order. Go from 1 to 16, and as you go, ask yourself, is it a perfect square? Is it an even number? If it's neither, it goes out in this space out here. If it's one or the other, then it goes in the space where they don't intersect. So maybe here, if it's just a perfect square, or here, if it's just an even number. If it happens to be both, if it fits both of them, like yes and yes, then of course we put it in the intersection, okay? So let's try this. So 1 is a perfect square because 1 times 1 is 1. But is 1 even? No, 1 is odd. So yes, it's a perfect square, but no, it's not even. So it works here, but it doesn't work here. So we put it in this space over here where they do not intersect. So 1 is going to go over here in just P. 2 is not a perfect square, okay? It is even though. So I can't put it in the intersection, but I can put it in the circle with E for even. 3, not a perfect square. It's also not even. So 3 does not fit either one. So it's not in the intersection. It's not in P or E. So that means it goes over here in the box, but not in either circle. 4 is a perfect square, okay, because 2 times 2 is 4. It's also even because it's a multiple of 2, right? 2, 4. So that means it goes in the intersection. So in the center where they overlap. 5 is not a perfect square, also not even. So it goes out here with 3. 6 is not a perfect square, but it is even, so it goes in the circle with 2. 7 is not a perfect square, not even, so it's going to go in the box, but not in the circles. 8 is not a perfect square, but it is even, so it goes in the E circle, but not in the intersection. 9, so 9 is actually a perfect square, because 3 times 3 is 9, but it's not even, so it doesn't go in the intersection, it goes where the 1 is. 10 is not a perfect square, but it is even, so I'll put it out here where 8 and 6 and 2 are. 11 is not either one. It's not a perfect square, nor is it even, so I'll put it out here in the box, not in the circles. 12 is even, but not a perfect square. 13 is not even or a perfect square. 14 is not a perfect square, but it is even. 15 is neither. And 16, last but not least, 16 is 4 times 4, so it is a perfect square. 16 is also even, so it goes in this intersection in here. Okay. So now I have them all where they go. Okay, I have them all where they go. So this is important. So every single value in the universal set exists in this box now, okay, in one of 4 places. They either exist in U but not in P or E, so that's over here. Okay, this space over here. Some of them exist in P alone, not in P and not in E, right? Some of them exist in E, but not in P. And some of them exist in both, okay? So just keep in mind, these values inside P all count as an element of P. So P has 4 elements, 1, 9, 4, and 16. Okay, everything in the E circle counts as an element of E, even if it's in the intersection. So it has 1, 2, 3, 4, 5, 6, 7, 8 elements. Okay, the intersection itself is really easy to see. It has 2 elements. And then the neither in P nor E is these elements out here, 1, 2, 3, 4, 5, 6. All right, so now let's answer the questions below. The first one is P, and it looks like P prime, right? So that is the complement of P. That is the complement of P. That's everything that is not in P. So remember, P has 4 elements. P has 4 elements. 4, 16, 9, and 1. Those are inside of P. So for P complement, it's going to be everything except for those 4 numbers. Everything else except for those 4 numbers. So this is going to be not 1, but 2, 3, not 4. I'm skipping that. Remember, I'm skipping everything that is in this P circle. So I'm skipping 4. Okay, so not 4, 5, 6, 7, 8, skipping 9 because it's in the P circle, 10, 11, 12, 13, 14, 15, skipping 16 because it's in the P circle. Okay, so I should skip 1, 9, 4, and 16. Let's double check. So these 4 cannot be in the complement. 1's not there, 9's not there, 4's not there, 16's not there. Okay. Now for E complement, it's the same thing. I'm going to put everything except what's in here, which is a lot more stuff, so be careful here. I'm gonna put all the rest of these numbers. So I'm going to put all of these numbers. Okay? So 1, 9, and then everything that's in the box outside the circles. Okay? All right, so let's go ahead and do that. So for that E complement, it's going to be basically all the odds, right? Because odds are what's not even. So it's going to be 1, and then 3, 5, 7, 9, 11, 13, 15. That one was pretty easy because it's everything that's odd, okay? So all of these here. Now, this one is P, and that looks like a U. So that's the union. So this is the union. Okay, that's everything that's possible in P or in E. Anything that's in either circle. In either circle. Okay, so I'm just going to look at my Venn diagram and write everything in order that's in either one. 1 is in one of the circles. 2 is also in one of the circles. 3 is not in a circle at all, so skip it. 4 is, 5 is not. 6 is, 7 is not. 8 is, 9 is as well because 9's in P. 10 is, 11 is not. 12 is, 13 is not. 14 is, 15 is not, and 16 is. So all of these values are in one of these 2 circles. Okay, in one of these 2 circles. And the last but not least is going to be the intersection. The intersection, in my opinion, is the easiest one to see. It's what they have in common. The intersection is so easy to see. Hold on, let me finish writing this. So the intersection is going to be what they have in common. And in this case, when it's a Venn diagram, you just look at where those 2 circles overlap. So that's 4 and 16. So 4 and 16 are the 2 elements that are perfect squares and even, that are in our universal set. Okay? All right, thanks for watching, everybody. Have a great day.